Hi everybody, my name is Joey. I gave a presentation, as Richard mentioned, a couple of times at HHC before and showed different calculator projects that I've worked on. So today I want to give an update on the main project I was working on last time I was here and then talk about two new things I've worked on. So the first thing I want to show is not a calculator, but it is related to calculators in a roundabout way. It's a little robot, and when you turn it on, it just blinks its eyes on and off, as you can see here. So as far as robots go, it's not very useful. I think it would qualify as a useless machine, like this box with a switch on it. When you press the switch, a finger comes out to turn the switch off. So a machine that only exists to turn itself off is not useful, but it's kind of funny to think about, and I think it's interesting, which was the goal for this little robot project. So as I mentioned, it just blinks its eyes on and off, and you could do that with a 555 timer, which would be really straightforward, but I didn't do that. Instead, I used a microcontroller. And the program could be really simple. You just have to turn the lights on and turn them off and do this forever. The problem with this, though, is that the microcontroller is a PIC32 that runs at 50 megahertz, which can do this 4 million times per second. So it's too fast for your eyes to see the individual on and off blinks. So what you could do is add a delay statement and keep it on for half a second and off for half a second. But I didn't do that. So here's what I did. Instead of having the blinking program run on the MIPS processor, which is what is in the microcontroller, I built an emulator for the 6502, which is an old processor I talked about in my prior presentations. And then I made a blinky program to run on that processor. So if you guys know anything about emulators or virtual machines, you know that they can introduce a tremendous amount of overhead. And so this doesn't blink at 4 million times a second anymore. It only blinks at a few 100,000 times per second. Which is still too fast to see, but is progress because we've been able to slow the blink rate down. So after I finished that, I built a second emulator that runs on the 6502 and emulates the 6502. So now I can blink the LED in an emulator inside of an emulator, and this is really, really slow. This is hundreds of times slower than running it natively. So I can tell you a little bit about this emulator that runs on the 6502. Here's a little ball bouncing program I made to test the functionality of the emulator. Once I had the emulator working correctly, I had it bounce 8 balls at the same time. And so this is not using 8 copies of the ball bouncing program and 8 copies of the emulator. It's only using 1 copy and keeping 8 copies of the variables that the emulator needs. And the way I'm able to do this is the way I have the memory set up. Usually with an emulator, you have a host which is doing the emulating that has more resources than the target. Usually it has more memory. But in this case, the host and the target overlap on their memory range. So the host can see everything that the target can, as normal, but the target can also see everything the host can, which means that the emulated system can see its own emulator, which means that it can also emulate its own emulator, which means we can do 3 layers of emulation, and this is really super, super slow, thousands of times slower than doing it natively. And so once we're to the point we can put emulators in emulators, we can do this to arbitrary levels, and it turns out if you do 6 layers deep, it will slow it down slow enough that you can see the on and off blinks. So as promised, it's not anything useful, but it's kind of funny, and I thought it was pretty interesting. So I thought about that. I thought about doing all different processors, but it was already a lot of work just to do one processor. And then here's another little tool that I made to help me along when I was building this. You can type in a little program here, and if you go more than 1 second without typing, it will assemble the program and show you the bytes, and then it will show you the program running on the right. So that's kind of a convenient thing. And interestingly, even though it's a Python program, it will also run in a browser window on my website, so you don't have to download anything if you want to try it. Okay. So the next thing I want to talk about is something I presented on 2 years ago when I was here. This is a calculator that I'm still working on building. I don't want to repeat my presentation from last time, so just a quick summary of this. It uses 6507, which is a cut-down, cost-reduced version of the 6502 from the 1970s, which is a very power-hungry, very slow processor. And the reason I'm using such a terrible processor to build this is that there was a competition on the 6502 forum to see who could build interesting things out of this chip. And I signed up to build a calculator because that's what I'm interested in. It has only 2 kilobytes of RAM and 8 kilobytes of ROM, and it's programmable in Forth, which as we know is linguistically closely related to our RPL and RPN languages we have on our calculators. I also showed that on my website I have an emulator so you can try out the firmware in your browser if you like. Okay, so here's where I was at HHC in 2021, the last time I was here. As I explained, I had an 8K ROM chip, but the firmware takes 9 kilobytes, so I need some way to make it smaller and fit. And so my plan at the time was to implement a small Forth interpreter so that I could rewrite some of the code from assembly into Forth, which would make it run slower, but it would save space. So here's an example of the system I came up with. On the top, I have assembly language, and then on the bottom in purple is the Forth. So you'll notice that I didn't have separate assembly and Forth files. I embedded the Forth directly into the assembly, which was really convenient. And then before I assembled the file, I would use Python to spot any of this Forth code and then translate it into bytes that are interpreted at runtime by the interpreter. So here's just a few things about the Forth system I came up with. As I mentioned, it's pre-processed with Python. It's token-based, so the different ways there are to construct a Forth interpreter, this is the one that saves the most space at the cost of speed. It's interoperable with assembly, as I mentioned. You can jump between the two pretty seamlessly. And I also, I also found a way to support forward references. Since in assembly, sometimes you need to jump to something that hasn't been defined yet, whereas in Forth, that's not allowed. So I found a way for the two to cooperate. And then I also used a lot of 8-bit data types just to make things smaller and faster. And another thing I did that was pretty cool is every time I processed the assembly file, I output this little debug file in HTML so I can keep track of what I've used and hopefully optimize to make things smaller. So here again is the same slide I showed before. I started to build my interpreter, and my plan was to make this as small as I possibly could. So I'd have as much room as possible to add Forth code and reduce the size of the assembly. Once I had that implemented, I started to rewrite it. So this yellow on the top you can see is Forth code, and then the blue you can see has reduced in size because for every byte of Forth code I can eliminate about 2 bytes of assembly. But unfortunately I had to add a lot of functionality to the interpreter. So this was not, I did not gain space doing this. So I continued that process, and I rewrote more of it, and the interpreter continued to get bigger and bigger. So at this point, I kind of took stock and said, if I were to continue this process and keep the same size interpreter, how much Forth would I have to write to get it to fit? And it would look like this. So I would have less than 4 kilobytes for all of the assembly, which includes the floating point routines, which is just not enough space. So this was a really fun project, and I feel like I learned a lot on this part of it. But ultimately it wasn't the right solution to get it to fit onto the memory chip. So I thought about maybe reducing some of the functionality, but since I already have showed that on my website, I didn't want to do that. So I decided I would just cheat and break the rules of the competition because the competition ended years ago, and I'm just finishing my entry because I like to do it. So that's how I solved that problem. One of the new things that I implemented was a little browser where you can see the commands that are built into the calculator and see the size of them. You can also look at the commands that the user can define and also variables. And also from this screen you can delete commands and variables as well, and it's garbage collected. So if you create a variable, for example, and then you access it from a program, and then you delete the variable and try to run the program, it will gracefully catch that and not crash the calculator. And then here is the hardware that I've built since last time. I had a small board that I showed before that wouldn't fit everything on it. And so I built a bigger one where everything will fit, and it's just in 2 parts here. These kind of fit together. And then also I had hoped by this point to also build a really small calculator running the emulator from the robot, because you may have noticed that the processor in this is the same processor that the robot is emulating, and that's actually the reason why I wanted to build a robot, is so I could build an emulator to emulate this calculator. So maybe next time I'll be able to do that. Okay, and the last thing I want to show is about calculator keypads. So I've noticed in the projects that I've done and other interesting projects other people have done that a lot of times people are able to make a circuit board for their hobby projects and they're able to write the firmware, but it's the keypads that really seem to be difficult for people. So what I did was I tried every way I could think of to build a keypad, and I want to show the results. But before I show that, here's a quote. I have not failed, I've just found 10,000 ways that won't work. So this is mostly a presentation about what didn't work, and then a few things that I think work really well. So before I show you the things I tried, I did want to mention a few things you can do that are less involved. One thing you could do is to get a label maker to make these kind of red and black labels here. You see this a lot on hobby projects on the internet. You can also try putting the label directly on the silk screen if you're making a circuit board. And you can also get these 12 millimeter switches, which have a transparent cap you can put your label under. These work pretty well, but since they're 12 millimeters wide, you can't really get a lot of them on a small keypad. So for what I tried, I built this design on the left using the SVG file format. I'm not very artistic and I'm not good at drawing things by hand, but with this format, it's just a text file where you specify the coordinates for all of your shapes and your letters. For the three-dimensional part, I used OpenSCAD, which follows a similar philosophy. You just write out a program to describe the shapes. You don't have to click or manipulate anything in 3 dimensions. And here's the model that I used for most of the tests. It's just a collection of simple rectangular shapes. And once you save this, you can print it out on a 3D printer for about 30 cents. So one of the things I tried to get labels onto the keys was to use these plastic cards. I looked at doing this a couple of years ago, and the places I looked at had a minimum of 250, so it wasn't very cost effective. But I found a place local to where I live that will print these off for $2 each. So for $4, you get enough labels for 1 calculator. I tried to cut this with a pair of scissors. You can see on the right that the edge curves in a little bit, and on the left it curves out a little. That's because when you cut the plastic with scissors, it tends to rotate as you cut it, which makes it hard to get a straight edge. So when that didn't work, I tried a whole bunch of other things. I tried cutting it with a razor blade and a hammer, and you could see the blade crack the first time I tried that, so that's not a good idea. And then I built a brace on my 3D printer for razor blades. I upgraded from a razor blade to a planer blade, which is used in woodworking. I also had leather punches custom made that will punch through a plastic card, but as you can see, they cause the card to crack. I also tried to build a guide for the cuts into the plastic card, and I also tried to cut 1 corner of the card off at a time. All of those did not work. Another thing I tried was to use a Dremel. You can see here at the bottom, the cut is okay, but it's actually hard to get a consistently straight cut if you do this freehand. So I tried using a piece of metal to guide my Dremel cuts. And you can see it works okay, but there are a couple of places where it cuts too much off of the face, and then here where it doesn't cut off quite enough, so I don't think this is a really reliable way to do it. One thing I found that I thought was really interesting is if you build a simple 2-dimensional shape like this, there are some websites where when you upload it, they'll show you a 3-dimensional preview of what it would look like to have that fabricated in metal. So if you wanted to make like a jig to guide your cuts, that would be one way you could do it. I also tried to have this plastic card cut on a laser cutter. After the company cut it for me, they informed me that it's made out of PVC, which you cannot cut on a laser cutter because it produces toxic gases. But they went ahead and cut it anyway, I guess, so they wouldn't have to give me a refund. So you can see on the left that the cut is pretty straight, but by the time we get out here to the side, it's off and it cuts these 2 letters off. That's because the company that prints the card, or the machine that they have, doesn't print it off exactly at the right dimensions. So I talked to them, and they gave me a specific size that my design needs to be, so I kind of redid that. But this was actually even worse. This was actually even more out of the right size. Okay, so what I tried that did work is a company called Vistaprint, which is well known for making business cards, but they will also make plastic cards. I put all of my labels onto 1 card, and I got 50 of these for about $40. It was pretty price effective. As far as cutting the cards, I built this little guillotine-type device on my 3D printer with a planer blade. It will not cut through the normal thickness cards, but you can get 0.25 millimeter cards on Amazon that this will cut through in one strike. And then to cut the cards, I built a brace on my 3D printer and glued it to my paper cutter. This Gorilla Glue really bubbles up and looks ugly, but it works, it's effective. You can see here that this result is maybe not perfect, but this is, in my opinion, a pretty good way to do it. You get pretty straight cuts doing it like this. So once I had those labels, I worked on rows of keys that I could attach them to. So I tried putting an indentation in there that I can put the labels down inside. I also tried gluing them on, and I left these 4 holes to pour glue in. And then I also tried to print off a little cap that will sit on top of it to keep the label on. and this is the one that I think works the best. Okay, another thing I tried was to use overhead transparencies. These are printed with an inkjet printer. As you can see, the super glue that holds these on causes the ink to run, so that doesn't work so well. I also tried using a different type of transparency that's built for toner printers. And so I glued this row of keys on upside down so that any excess super glue would stay on the transparency and not drip down the side of the keys. But when the glue dried, the transparency fell completely off and it didn't stick at all. And the interesting thing though is that all of the ink stayed on the key and it's held on there with the super glue. So I'm not sure over time if this would be a durable solution, but it was interesting and unexpected. I also tried other types of glue, which didn't work. And then I tried to cut the transparency with a pair of scissors. But if you make this slightly too small, the transparency will shift underneath of the keycap, which is kind of disconcerting. And then another thing that was really interesting was I found a project someone else had done where they had printed with a 3D printer directly onto a piece of toner transparency so that the hot plastic would absorb the toner ink. And they got a really good result out of that. I tried with much, much smaller text as you see here, and it worked okay, but it was pretty easy to scrape the toner off, as you can see when I tested. So I don't think it's that durable. So one thing I tried that I did have a lot of success with is dye sublimation. You can buy these sheets of special paper that are printed in dye sublimation ink. When you heat this to a particular temperature, it will sublimate, which means it goes from a solid to a gas without becoming a liquid. And plastic will absorb that gas really, really well. And because there's no layer of paint or ink on top of the plastic to wear off, it's a very permanent way to put labels onto plastic. I also bought this little iron, which is specially made for this process. So when I got this working, I tried to sublimate on all types of plastic. I got just plain white cards. You can see here it's a pretty good result, but in some places the letters are a little bit fainter. That's because the little iron is not big enough to do one card at once, so you have to do it in pieces, which makes it difficult to get a consistent result. I also tried to sublimate onto regular plastic that you use in a 3D printer, which has a low melting temperature, which is great for 3D printing, but is bad for labels because it will squash flat like a pancake. Another thing I tried was to 3D print directly onto the sublimation paper in the hopes that the heat would cause it to sublimate, but it didn't work out so well. And then I sublimated on transparency, which is a really sharp result, but you still have the problem of how are you going to cut that accurately. So here's something I tried that worked really well. This on the left is acrylic that's cut on a laser. And unlike PVC, it does not release toxic fumes when you cut it. You get really smooth, straight edges when you do this. This particular piece of acrylic is kind of translucent. It's not completely opaque, so you get kind of fuzzy edges on the letters, as you see here. So I experimented and found a better piece, and the trick is to buy a piece of acrylic that's specifically sold as made for the sublimation process. So that is a lot sharper looking. And that is actually the ones I have on the calculator that I just showed. I can pass this around if you guys want to see. You can look at that if you want to. And another thing that you can try is to change the type of plastic in the 3D printer. If you use a PETG or PETG, it has a much higher melting point, so it retains its shape when you heat it up enough for the dye to sublimate. Another thing I tried is to use a Cricut machine. This is a printer, and instead of having an ink cartridge in the head, it has a holder for a special pen. You can buy things like glitter inks and metallic inks. My wife has one of these for like birthday cards and invitations. And you can buy pens that hold sublimation ink. It also has a blade on the end, and here is an example of the cut. It's not bad, but it takes a lot of passes to cut through the plastic, and it's not exactly straight. You can also send designs to the printer, but it will not print off any text that's in an SVG file. So if you want text, you can make your own out of lines. And so it's not that sharp, but I can confirm that this ink will sublimate really well on plastic. Another thing I tried that worked really well was to use cast plastic. So you can buy a 2-part liquid plastic. When you mix those together, it will get really hot. And then you have a limited amount of time to pour the plastic into a silicone mold. And after the plastic sets, the part you get out is really, really nice. It's a lot better than what you could make on a 3D printer. So here's what I tried. I 3D printed a box with a row of keys. And then I poured silicone into this, and then when that set, I printed another box around it for some stability. And then I poured plastic into here. Because this is what is called an open-faced mold, a one-part mold. When the plastic goes in, because it's a liquid, there's surface tension, which means that when the part sets, it's curved on the back. It's also difficult to get a consistent amount of plastic into the mold, so you end up with rows of keys that are round and not all the same size. So to fix that, I built a two-part mold, which is actually a very complicated topic. You could, give a very long presentation on that, but just long story short, I put a hole in the bottom to pour the plastic into, and then I placed these 5 holes strategically so that as the plastic fills up the mold, the air can escape and no bubbles will be caught in the plastic. And the result of this is pretty good. You can see here that it's a little bit warped on the edge from where I did it, but I think with a little bit of tweaking, I could get really perfect rows of keys with this method. Another thing I tried was to print raised text with my printer. I'll just skip over this. Long story short, you need a small nozzle, and even then it didn't work very well. Another thing I tried was to build hollow keys so that I could pour plastic in from the back to get the same effect as a double shot key. On the type of printer I have that deposits hot plastic, it's tough to get these fine details right. So I had someone online print it off with an SLA printer, which uses a liquid plastic that's sensitive to UV light and lets you do a lot higher detail. When I got the parts, they look good on the front, but on the back, the slots I had left to pour the plastic in were mostly closed. And I don't know if this is something that's common with this type of printing or if it was just this run. But I think if I could figure this out, you could have essentially a double shot key with this method. And then another thing I tried was to manually stop my printer at a certain point in the print and then change out the colors to print in white. But again, it's just tough to get those details on that type of printer. There are, however, printers that are made to print in several colors. There's one that will print with 4 colors and you don't have to change it. The machine will change it for you. And then you get a lot better results. Dave said Bamboo. That's exactly what kind of printer that is, Bamboo X1. So this was on a company. It was a person online who was printing things off. And I think it's tough to get a consistent result. You can see here that it strings a little bit between the letters. So the divide key looks a bit more like a diamond. And for example, the semicolon is not exactly crisp. But I think if you tweak this, you might get a good result doing it this way.
Joey, do you know what diameter nozzle? Was that printed with a 0.4 nozzle or a 0.2? Do you know?
0.2,
Okay.
yeah. And then the last thing I want to show is if you, instead of looking at consumer 3D printers, you can look at commercial services that will print them using a different technology. The one on the left is printed with a process called MJF. As I understand it, they use a plastic powder that they melt with a laser. You can see that the letters came out a little bit faint and the surface of this is rough. It's in the box that's passing around. They warn you when you buy it that the surface will be rough, and they offer to smooth it for a fee, but the part was too small to qualify for the smoothing. And then on the right is a different process called HDFC, which is a bit more expensive, but I think it looks really good. So that's it for all the stuff that I tried. There's a couple of other things that you could try. I think with cast plastic, you could do a double shot type key. There's also a lot of stuff that can be done with lasers, either marking the plastic or cutting the plastic, either to build a master that you would cast or to laser in maybe letters that could be filled with plastic. I think you could do some of that with CNC machining, and I've also seen people make them out of metal circuit boards, which nowadays you can buy circuit boards where the substrate is not fiberglass, but it's aluminum, and they do that to dissipate heat for things like LEDs. But nothing is stopping you from building a keypad out of that. So I know that's a ton of information. Yes?
What about 3D printing?
Yeah, some of those were 3D. Those are 3D printed, yeah. And so I know that was a huge amount of information. So just to summarize, my favorite way of doing it is to use a 3D printer with a PETG plastic and dye sublimate. What I think offers the best quality by far, but is also really difficult, is to cast plastic and dye sublimate. Other things you can try that are good quality and a lot less difficult are to cut up a plastic card or to laser cut a piece of acrylic. And then what is the easiest, since you don't have to invest in anything, is just to use a process like HDFC and then have a company make it for you. So that's it. thank you for your attention. If anyone has any questions or you ever want to build your own calculator, you're welcome to email me and I'll help you however I can.
You have, being a fourth person, you have floating point in this machine, or
Yes,
you
it
do
does.
the fourth way?
No, so I say it's fourth, but there are a couple of compromises. So there are types. There are 4 different data types, which usually in fourth you don't have that. You may have a separate stack for floats, but it's usually one type. But here I have pointers, which are 16-bit, floating point, and then I have strings up to 8 characters. Okay, thanks.